All right, so so what we see here is that how do you draw these dipole moments? The arrow goes which way? Which way is the arrow going? Toward what? Toward,
right.
well, I could flip this around. So toward, yeah, why? Yes, it always goes toward the thing where the electrons are going to spend more of their time. You got that? And then that leaves the other end of the arrow with a plus sign. So that's called a dipole moment. Pretty easy. Now, because there's only one bond in hydrogen fluoride, then we can also say that the entire molecule would be polar. So the bond is polar covalent. Is the molecule going to have an end of it that's plus and another end of minus? And the answer is yes, okay? Because you only have one dipole moment, and that means it's going to be polar. Now let's take a look at water again. And the difference here, hydrogen was 2.4 and oxygen is 3.5, a difference of about 1.4. Is that a polar covalent bond? What do you think? Remember the chart? It's bigger than 0, right? So it's going to be polar covalent. But what about the other bond between the hydrogen and oxygen? The other hydrogen and oxygen, what is it going to be? Is it going to be polar covalent also? Okay, so now we have two polar covalent bonds. But will the molecule be polar? And it is, that's a very astute, Clay, yesterday. He said, it's like vectors. It is. This dipole moment is going that way. This dipole moment is going that way. What does this vector plus that vector give you? It gives you that vector, doesn't it? Is that right? What's this plus this? All right, so anyway, is there a net dipole moment? That's when you add them all together. Say yes. And if it has a net dipole moment, I would expect the water molecule to be a what kind of molecule? Polar. Now, this is kind of fancy graphics. It's computer graphics. They simply told the computer to use false color imaging. It says, if the electrons are spending a lot of time there, make it orangish. If they're not spending a lot of time, make it blue. And it makes a picture that you can actually look at. They did this with planets before. I've never seen a picture in a magazine of Saturn, and it was like blue and red and orange. I said, wow, is that what it looks like? No. No. As a matter of fact, Saturn's all butterscotch looking, the whole thing. So where'd they get that picture? They had a band of butterscotch, which was a little different density than another one. So he told the computer, that color of butterscotch, make it orange, and put blue next to it so humans can actually tell how many bands there are in that planet's atmosphere. So anyway, it's called false color imaging, and I don't know if you've heard that before. Let's do, and by the way, all the models I'm using in the book, those are the ones I have on the test. Is that okay? Make it easy for you? If I have one that's not on there, you'll be able to guess it. But all right, how about NH3? What is NH3? What's the word for NH3?
Ammonium.
Ammonia, right? Not ammonium, but ammonia. It's a compound. All right, ready? Let's try it. It just so happens that it's shaped like this. Okay, so imagine here's your nitrogen, hydrogen, hydrogen, hydrogen. Everybody see that? It's kind of a funny shape. It's like 3 legs and a little nitrogen sitting there. Okay, what kind of bond would you expect between this hydrogen and nitrogen? Hydrogen is 2.1. What's nitrogen? 3.0. What's the difference? 0.9. You're definitely into the polar covalent bond, right? Let's do a dipole moment. I'll do another one. I'll do another one. Okay, ready? What's this plus this plus this? This. So, would ammonia be a polar molecule?
Sure would.
It would. It has a net dipole moment. And net just means you add them all together, right?
Yes.
All right, can you do one? I'm going to cover that up. Sit with somebody and see. I'll give you a clue. Carbon dioxide is like this. Carbon, double bond O, double bond O, okay? So try carbon dioxide, and I'll tell you what, yeah, let's do that. See if you can do carbon dioxide without looking in the book, and tell me about the bonds and tell me about the molecule. Okay, let's try it.
So, can we use the graph?
Oh, yeah.
Here. So,
carbon is 2.5 and diphos. Oxygen. So and oxygen is 3.5.
Oh, oxygen is 3.5, so it'd be 7 total?
Yeah, I think so. Is that how you do it? Yeah.
Oh, wait, you know what? I just remember that on one of the packets I gave you, you actually have a picture. Oh, you don't have this
I don't
one.
have
though.
that.
That's right, you don't have this one. There you go. There you go. Everybody has that.
I guess. Actually, I've seen that, so yeah. Oh yeah, I think I still use that for.
All right, here we go.
What is, you don't have that, oh, 3.4.
Alright, so the difference from 7 to 6.5.
So this is kind of an interesting one.
2.5 minus 6.8. Moles.
Talk it out, okay? Talk it out.
I think it's a non-polar molecule.
So,
Yeah, but it has 4 polar covalent bonds in it.
That's crazy.
big three.
Yes.
All right, everybody look up here. And let's take a look. Carbon is 2.5, oxygen is 3.5. The
Yep.
difference electronegativity is 1. That's kind of up there.
But that's.
So that means let's draw a dipole moment. Which way does the arrow go?
Big eight.
And don't say to the right. Say toward what? Toward oxygen. Why? It's more electronegative. All right, so I draw that, and there we go. And I draw this one. Matter of fact, it's actually a double bond, and so I could draw 2 more.
Oh, that's how you do
Okay, now, ready? What is the net dipole moment? Add those vectors together.
0.
0. So even though it has 4 polar covalent bonds in it, the whole molecule has a net dipole moment of 0. So it's a non-polar. Yes.
How do we know how the bonds are going to work?
I had to tell you.
Okay.
But in the second semester, we actually do a little organic chemistry, and you'll actually see how to make carbon dioxide, and you'll know it's a double bond. I had to tell you. So I'll draw it for you. Good question. Now,
Why is carbon bigger than oxygen?
Because carbon is the bigger.
well, bigger or more, it's less electronegative. Is that what you mean?
Well, I mean, like in the diagram, like the black ball is bigger, but
Oh, I see.
oxygen is more.
I would have to look that up because I don't have the atomic diameters memorized.
Extra.
Let me think about it. I do know as you go left to right, the size of the atoms actually get a little smaller.
Oh.
So actually, when you go down a period, atoms always get bigger because you're adding new energy levels. But if you go left to right, they actually get smaller.
It makes sense.
So actually, oxygen should be smaller than carbon. I don't know the number, but it should be smaller.
Do you think that's why
And so-
electromagnetic increases because it's smaller, so it can weasel its way in?
That's a great question. What a great question. What is it that makes one nuclei, one atom, draw the pair of electrons onto it more than another? They both want them. They both want to share them.
I don't want to steal Mason's
Does
answer.
you know? I've never read that. I like what you said. Is it possible that the smaller atom does it have? Why would it have more capacity to draw the electron? That's a good question. I don't think I know the answer to that. Does size matter with electronegativity? That'd be a great thing to look up. What a great question. You made my day. You made my day. Well, actually, the third graders made my day, but you also made my day. So, all right, let's do another one. Let's do another one. The next one I'd like you to try is, I'm going to show you this little chart here. Look at this chart. Here we go. If you have linear molecules, and HF was linear, carbon dioxide was linear, then what if it's in that arrangement, like BAB, like carbon dioxide was that way, wasn't it? OCO? Then it tends to be no net dipole moment, nonpolar. And what about planar? What's planar mean? Yes, in the same plane. You get that?
Yeah.
Now, if it's planar, And what if the bonds are about 120 degrees away from each other? What would this plus this equal if it was flat?
Not that.
0. What if I go the other way? What about that plus that plus that? It's still 0.
Cause
So that also would be, now, the example of that one is SO3. SO3 is flat. It's flat, and the arrows, which one? Look up sulfur and oxygen. Look who's more electronegative, sulfur or oxygen?
Why is it
Oxygen?
called the bond stick model?
oxygen.
Okay, oxygen, right? So right, see this right here? So the dipole moments would look like this and that and that. And what is this plus that equal? 0. So that's also be nonpolar. And now this one's called tetrahedral. Now a tetrahedron is not a pyramid. A pyramid has a square base, and a tetrahedron has a triangular base. Okay, this is a really big shape in chemistry. Now take a look. A tetrahedron, and I should have got my ball and stick them all out.
What's that?
Ball and stick is the balls are the atoms, the sticks are the covalent bonds. And I should have gotten it out. I'll get it out. Anyway, we're going to do a lot with those in the second semester. But take a look at carbon there. See where it says CH4? Everybody see that? Look right here. See where it says CH4? There's carbon. And a tetrahedron is where the carbon's in the center, and it hydrogen up, hydrogen, 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 like that. And it forms a tetrahedron. And this is found a lot in chemistry. What do you think would happen to the net dipole moment there?
0.
So look at this. Which one's more electronegative, hydrogen or carbon?
Carbon.
Okay. And so the arrows go. Wait, you sure?
Well, are you counting the 4?
Oh, I'm sorry. I'm doing CCl4. My fault. Not CH4, but CCl4. Sorry.
Oh. Then CL.
Okay. So which way the arrow is going to go?
CL. So right.
So this one goes from the middle. From here, it goes this way. This one goes this way. This one goes that way. Uh-oh. What's the net dipole moment on a tetrahedron like that?
0.
It's also 0.
Probably when
Now, the one I thought was interesting was ammonia, because ammonia, you think it's flat, but it's not flat. It actually goes like this, doesn't it? Like that. So that's not really planar. It's not planar. All right, next one. I want you to do hydrochloric, HCl, hydrogen chloride. Try hydrogen chloride. Hydrogen chloride.
Hydrogen is 2. I can't read that.
Okay. And I'll make sure you can read it when it.
I think it's 2.1.
Hydrogen 2.1.
And what was the other one?
Chlorine is up there pretty high,
3.0.
probably. 3.0. All right, so what do you think? With the hydrogen chloride molecule, would it be a polar molecule?
Yes.
Yes.
For real.
Well, first of all, there's only one bond, so you only have one dipole moment, right? So that is the net dipole moment also. So does it have a net dipole moment?
Yes.
Okay, so it would be polar. And the last one, I don't think there's another one. Oh, here's another one. Let's flip the page. Let's do hydrogen sulfide. Let's do hydrogen sulfide. Here's what it looks like.
It's 2.5.
Here's what it looks like. Hydrogen sulfide. See if you can do that one.
Is you at the
So what's the be?
2.1
All right,
sulfide.
sorry. Hydrogen sulfide.
What is sulfur's number?
And I will tell you that this is what it looks like right here. This is what it looks like.
And what's the charge of sulfide?
Sulfur.
So it's gonna have a net
Shut up.
Not ever talk.
I need to finish.
All right. So which way do I draw the arrows? Do I draw H toward S or S toward H? Who's more electronegative?
Sulfur.
Okay, so I'm gonna draw it toward sulfur, right? And I'll draw this one toward sulfur. Now, what about the net dipole moment.
It's gonna be down,
It is.
yeah.
And so therefore, would you say hydrogen sulfide is a polar or a non-polar?
I'd say it's pretty polar.
It's
to me.
Okay.
polar.
Yeah, it's pretty
I
polar.
noticed that in your homework, one of the first questions, I actually haven't completely done that, so let's take a look at this right here. Which of the following are miscible and which ones are not, and give a reason. I can tell you right now that whether something dissolves or not has to do with polar or non-polar. It has a great deal to do with it. And so let me give you a little hint here, okay? If you can identify this, can you identify this as an ionic compound? Can you identify this is the metal ion, this is a non-metal ion, it's a polyatomic ion, but can you understand this is ionic?
Yes.
Okay, so it has a plus minus nature to it. What about this guy? KCl.
That's ionic. That's
Yeah.
ionic.
So it says here,
They're all.
would
ionic.
these two tend to dissolve? Yes, and I have a chart that even tells me the ones that don't dissolve, but they do dissolve. But then let's go over here to something a little bit harder. This right here, I don't teach organic till the second semester, but I will tell you that alcohols. I'm gonna draw this out for you. Wait a minute.
We talking about H2?
Let's see. Let me think about that one for you. I don't know if I don't want to put that on the test. I don't want to put that on the test. Alcohols. I'm gonna draw an alcohol for you. Alcohols are distinguished. They have carbon, hydrogen, oxygen, but they always have a carbon attached to an OH. Everybody see that? That makes it an alcohol.
Isopropyl.
Okay. No, this was methanol. That's right.
Ah,
But anyway, what we have here is, guess what kind of bond is between these two? See here, the electronegativity difference is pretty small. But what about here?
that looks like an ionic.
And anytime oxygen or nitrogen or chlorine, if they get hooked up with hydrogen, who always gets the short end of the stick? Hydrogen always gets the short end of the stick, and so there's going to be a polar bond right here. So alcohols have they're polar in nature. Now, so what happens is, this part here makes it polar. Now, what is water? Is water polar?
Yes.
So do alcohols dissolve in water? Yes. Let's go down to here. What about, and this is how they made an alcohol. See that? See how they ended it with OH? Okay, that's an alcohol and water. Are they going to mix? Yes. This is interesting here. This is called a hydrocarbon. Hydrocarbons are non-polar. The difference between carbon and hydrogen is so small, and it's a very symmetric molecule, that hydrocarbons do, like gasoline, vegetable oil, they do not mix with water. Likes dissolve likes. And this is non-polar, this is polar. Next one. Hydrocarbon and what? Non-polar and what? Oh, I'm sorry. What about polar, non-polar and non-polar? Yes, they do mix. And how about this one? Ionic, that's plus and minus. Polar, plus and minus, right? And they mix. Is that what you're asking about?
Yeah.
Okay, so I don't think I actually went over that. Let's see. And the last thing I want to show you, I don't know if I want to put this on a test now. Let me think about that. I don't know if I want to show you. Well, I want to show it to you. I don't know if I want to go over it or not. Okay, I wanted to.
So whenever there's a hydroxide bond in it, it's almost always.
Okay, now, even though I can't teach all of organic right away, real quickly, ready? NaOH really is this ion and this ion. It really is the two different ions next to each other. But when you have COH, everybody see that? There are no ions here. So this is actually not hydroxide. This is hydroxide because you put it in water, it'll break off into a hydroxide ion. This will not come off. This will not come off. And so this makes an alcohol group and it won't come off. So it's not going to come off and it's not going to be a base. And so that's the difference. We actually don't even call it hydroxide there. Okay, Anyway, good question there. Now what I'm gonna do, I'm gonna spend about 10 minutes on this, and I'm not gonna overdo it, but it's kind of neat science. What I'm gonna do is I'm gonna read through here and look at this graph. Read through here and look at the graph. It's something you've never had before. And so I'll start reading, and then we'll have somebody else can read that, all right? Let's go down to what is a chemical bond? There's no simple and yet complete answer to that question. Even though I make it say in simple, maybe in 10th grade, it's not as simple as you think. Did you find out that we actually have covalent bonds and then polar covalent bonds? Anyway, and then we had ionic. Anyway, what it talks about down here, it says we can obtain energy about the strength of a bond by trying to break it. So let's say, hey, how strong is that bond? Well, let's add some energy to it and see if we can break it. And the amount of energy we think it takes to break the bond is probably how much energy was in that bond to begin with. All right, let's go down here. So why, earlier we saw when sodium chloride is dissolved in water, the resultant solution conducts electricity, a fact that helps us convince us that sodium chloride is actually composed of ions. Therefore, when sodium and chlorine react to form sodium chloride, electrons are transferred from the sodium to the chlorine to form these ions, which they aggregate and form solid sodium chloride. Now here's a big question. Why does this happen? And it says here, this is something you learn in college, the best answer is systems like to achieve the lowest possible energy by behaving this way. If it takes less energy to form ions and stay together, then guess what would happen if I put sodium and chlorine together? Would I have to add heat, or you think maybe heat would be given off? If it forms a compound that has less energy than the two things it started with, wouldn't it give off the heat, give off some kind of energy?
True.
Okay, then, anyway, and also there's an attraction between the positive and negative charges. Now, it just so happens that a guy named Coulomb, remember this guy?
Yep.
Anyway, that looks like a fancy equation, but what he really was saying is that the energy that exists, or the amount of attraction that exists between things that have different charges, is directly related to their charges. This is how much energy in there, and inversely proportional to the radius, the square of the radius. Now that looked like one of Newton's, do you remember Newton's universal gravitation? It was almost identical about who was directly proportional and that kind of thing. To make a long story short, I saw a cartoon the other day. It had Newton doing his work, and then Coulomb was looking over his shoulder, he's copying. So anyway, the Coulomb's law looks very much like Newton's that had to do with masses, mass and universal gravitation. Anyway, let's take a look over here, and let's see if we can figure out what happens in a covalent bond. Okay. Well, somebody start where it says, let's explore. Who wants to read this real quickly? Jeff, go ahead. Let's explore.
Let's explore this situation from a very simple point of view by considering the energy terms that result when two hydrogen atoms are brought close together, as shown in figure 8. When hydrogen atoms are brought close together, there are two unfavorable potential energy terms: proton-to-proton repulsion and electron-to-electron repulsion.
All right, stop right there. So you're going to bring these two hydrogen atoms together, right? You got two things acting against you. You want to bond together? You already got two strikes against you. What are the bad things that can happen? I'm trying to push them close together. What's going to stop you?
The repulsion of protons.
The positiveness and the positiveness, right? They're going to tend to repel each other. You're trying to bring them closer. And what else?
The negative.
The electron. You want to put them together? Yeah, just try. You better overcome that first, right? Keep going.
In one favorable term, proton to electron attraction. Under what conditions will the hydrogen molecule be favored over the separated hydrogen atoms? That is, what conditions will favor bond formation? The answer lies in the strong tendency in nature for any system to achieve the lowest possible energy. A bond will form, that is, the two hydrogen atoms will exist as a molecular unit
If
the system can lower its total energy in the process.
Go ahead.
In this case, then, the hydrogen atoms will position themselves so that the system will achieve the lowest possible energy. system will act to minimize the sum of the positive repulsive energy terms and the negative attractive energy term. The distance where the energy is minimal is called the bond length. Total energy of the system is a function of distance between the hydrogen nuclei as shown in figure 8.1.
All right,
Note
so-
several important features of this diagram.
Okay, now, so here we go, ready? This is pretty advanced. You can actually look up a chart and they estimated what's the bond length. If carbon forms a bond with hydrogen, is it a long bond or short? And that's how they end up knowing how molecules are shaped. But take a look at this graph, and so what happens if I bring these two hydrogen atoms really, really close to each other? What if the distance between them is 0? Then what's going to happen there? You're going to have a lot of what? A
Energy.
huge amount of what? Repulsion or attraction? You're going to have a huge amount of repulsion, okay, like that. What if I make them really far away from each other? What if they're really far away from each other? What do you think about that? Okay, so then almost no repulsion, right? Okay, but again, you don't have a compound, do you? So there's no bond. So what happens is you bring them closer and closer together. What happens? So take a look here. What happens when you get to about that 0.074 nanometers? So what's happening is they get close enough to attract each other from the attraction, but they're not so close to have a huge amount of repulsion. So here's a huge amount of repulsion. Here's like no attraction whatsoever. And then you get to this one sweet spot here. And this is the lowest energy that is available here. And that little trough right there is where they're going to form a bond. So are they still being repelled? Yes. Are they being attracted? Yes. But the minimum energy of this compound is right about here. It's kind of a compromise between repulsion and attraction. And that's how you get this thing called a bond length. And anyway, I don't want to put very much that on the test. I just want to show you that because we're talking about covalent bonds here. Okay, what do you think? Let me, I know tomorrow is a review day, but I'd like to show you, I know a hand wrote it, but I'll show you what I thought was on the test. Oops, here we go. Okay, let's go down here. Now it says here, the test, there's a huge multiple choice part, and those go a little faster, but let's take a look at the part that's not multiple choice. You're going to have a short answer that has to do with double replacement reactions. Now, what are the two kinds of double replacement reactions? What are the two kinds of double replacement? Precipitation. And so remember how we wrote those out? We wrote their chemical equation, then the complete ionic equation, remember that? And then the net ionic equation. So you'll have to do that to show me you can do that. And the other one I'm going to have is the one you did yesterday. What's that called? What's the, I'm sorry. What's the other double replacement? Sorry. Double replacement is either precipitation or what else? Or formation of water, right? What's that called?
Acid-base reaction.
Acid-base neutralization. All right, so we did some of that. Then I am going to have you do a redox where you have to do these half reactions. And we've done about 2 or 3 of those. And then the other one, I'm going to have drawings very similar to what was on the paper. And it'll ask you to draw the dipole moments, draw them the arrows the right direction. And then it'll say, now draw another arrow for the net dipole moment. Okay? All right, so I'm trying to spell it out for you. And there's one more section which is not bad. I'm going to give you some polyatomic ions or compounds, and I'll say, what's the oxidation state of each element in this compound? So let's try this one. NO2, nitrite is -1, isn't it? Nitrite, is that correct? If that's the polyatomic ion, nitrite, what's the oxidation state of oxygen in there? What number would you assign to oxygen? Uh-oh. And what is it? -2. If it's not a peroxide, oxygen has what oxidation state?
-2.
-2. And this is not a peroxide. Okay, so now, ready? So we'll put a little -2 there. But you have two of them. Each of them is -2, and you have two of them. That's -4. And the whole thing has to have a -1 charge, doesn't it? So what's the oxidation state of nitrogen?
+3.
Plus 3.
Yeah.
That's easy, isn't it?
Yeah.
Now let's do another one.
Isn't that the same thing?
Is it?
Yeah.
Is it?
Are you
To
sure
me
about
it is.
I don't think
I guess it's not. But I don't know how to do something.
Okay,
other
I'll
than
give you the
this.
name of this one. This is called the nitrite polyatomic ion.
Is that dinitrite?
No?
No,
High nitrate.
I'll give you a clue. It's not an ion because it doesn't have a charge.
says 0.
Nitrous dioxide.
Nitrogen dioxide, yes. Nitrogen dioxide, yes. Okay, now, what's the oxidation state of nitrogen in that? Each oxygen is -2. You have two of them. And the whole thing has to have a net charge of 0.
Oh, so it's
What do you think? Oh. Okay, so that should be not too bad. That section here, you had to do the complete ionic equation, net ionic equation, and then you have to do half reactions, and then you do these little drawings where you put net dipole moments and dipole moments, and then right there. That's the only part that's not multiple choice. Yes.
So when you have a compound that has, like, one compound dot another, what does that actually mean?
Okay. Okay. Great question.
Very good.
Okay. Now.
Yeah, we used that last year.
I would say this is very unusual. If you look it up, it'll say it's an unusual case. But there are many forms of this on the planet. They're called hydrated crystals. And what it means is, if I were doing the molar mass of that, I'd have to include it because 5 water molecules are locked up in that copper 2 sulfate crystal. And the experiment you did in 10th grade is where did you do that one? Okay. And you heated it up, a lot of steam was coming out of the test tube. But all you had was dry powder in there. You had this stuff in there. And the water was coming from this. You were driving the water out of the hydrated crystal. I'd have to look that up. I have not looked up the structure of a hydrated crystal as far as, is that what you're asking
So
about?
that's the hydrated crystals are the only time you ever see a dot in a compound?
That's the only time you'll see a dot.
Okay.
And we have, this is pentahydrate, there's hexahydrate, dihydrate. So, okay, good question. Now, the rest of them, I did count them. I counted them. The good news, you have a lot of questions that have to do with concentration. Now, that could be molarity. I might have one molality question, maybe one. So molarity, percent by mass, see that? You should be pretty good with that. How about the polarity-based questions, meaning, do you think that's polar or non-polar? Well, right now, what do you think about hydrocarbons? What are hydrocarbons? They only have hydrocarbon like gasoline and
Their fuel.
their fuels, paraffin.
They're not participating in
Yeah, the
bonding
difference in
reactions.
electronegativity is very small. They're always non-polar. And then ionic compounds have a plus-minus nature. Polar compounds have a plus-minus nature. All right, next. You'll have some redox questions that are multiple choice. Got it? Then you have 8 of those. And then you have solubility, net ionic equation, and you don't have to show your work, but they're multiple choice with 8 of those. Acid base, that's like a double replacement, right? Acid base neutralization. And remember the MA, VA, remember that? Okay. And then there's 5 others that are kind of mixed like that. All right, go ahead. Question.
Just forgot what my question was.
So,
What's the threshold for a polar molecule and not a polar molecule, like the number?
okay, now, unfortunately, some books don't like to lock it down. That's a problem. So I've looked at 3 or 4 different chemistry books. Some are close to 2. Most of them are close to 2. Did you know that most chemistry books don't give you this? Why not? Why don't they give you a chart like that? First of all, they want you to know the rules, the general rules like that. So that's number one. I think it could, if you had like, what if you had really concentrated that, not so concentrated that, is it possible you might get different results? I think so. This chart might have been made, everybody was 1 molar, maybe that's the way it was, but I rarely see this ever in a chemistry book, but why not? Seems pretty handy to me. What is your book going to do? It's just going to give you that right there, the general rules like that. Same thing here. I don't know exactly why. I don't think they like to lock in. They said if it's more than 2.0, it's ionic. Is this really ionic 2.1? I'm going to say ionic, but does it have at least a little bit of covalent nature to it? A little bit? Is there a little bit of tendency for that electron to come back? Yes. And so I think that's why they don't like to lock in the numbers. That's my opinion. If you want to look up different sources, see if you can find out at what electronegativity threshold would you consider ionic versus, and you might get a lot of gobbledygook, and they'd say, well, nothing's truly ionic, or you might do something like that. But if you can find some threshold numbers, I'll give you credit for that. You ever hear that question? That's a great question. We should do that all the time. Same thing here. I made up this number. I've seen some books that say somewhere about 0.5. If you're less than 0.5, you're kind of like covalent, not too polar at all. And then if you get past 0.5, it's polar covalent. All right, everybody okay on that? So here's the numbers that I've gotten by looking at a couple, 2 or 3 books. A lot of them don't like to lock it in. Got that? They don't like to lock it in.
So if you get a 3, you can pretty much assume that it's ionic.
I would say after 2, I'd say ionic, yeah. I'd say that. All right, I'm actually finished with everything. Yeah, I'm finished, really, so. Well, now, your advisory actually starts at 2:05. Wait a minute. I'm sorry, 2:10. But you get out here at 2:05. So I'm actually done. If you would like to leave, you can. So, all right, tomorrow, please be ready and to get in a group and help each other study a little bit. Okay.
Yeah, I got in there like 15 minutes into it, I was just late.
I wasn't late, I had something going on for a while, and we hadn't even started yet, and I had to go get the market.
I mean, to be fair, I did spy on the other class, but.
No, you were doing God's
Bye.
work.
Bye.
Can I take this?
Yeah.
Yeah.
We're doing God's work.
Everyone be happy.
Thank you, Mr. Danny.
Bye.
So I had a question,
Okay.
Just about this chart,
Okay.
the electronegativity chart.
Yeah, electronegativity. Uh-huh.
So I understand like what the numbers represent, but like, what are they? Like exactly, like what's, how do you get those?
Okay. Now let me see here.
Like, does it have to do with the valence of electrons? or
I gotta think. See if it's in here. That's a great question. How do they actually do the science? How did they get those numbers? And
Yeah.
they might have had some numbers and they made them all look nice. Like instead of 6.5 times 10 to the third, they still call that 1. Or, I mean, that's why you're getting such clean numbers there. 1, 3, like that.
Okay.
I'll tell you what. Can you look it up? I'll give you credit.
Sure.
Find out how did they get electronegativity numbers.
Okay.
And if you just print the article and I'll highlight some things on there, I remember looking that up 20 years ago.
Oh, okay.
But no one's asked me that since then,
Oh, wow.
so I forgot.
Cool.
So, but I know the numbers being that clean, they had to be some numbers, and they divide everybody by some other number and made them look like nice numbers like that.
Okay.
Because humans don't like weird looking numbers.
Yeah, exactly.
Yeah, if you can find out, I know I haven't read it for a long time.